So I had just a couple more examples of these Turing machines, and then we're going to have some time to talk about the test on Friday, review topics, whatever. We still do have homework due today. I hope you checked it out. Let's just do, like I said at the end last time, I had an example for you guys to try, although I don't like starting out with from nothing with trying out a hard example. So let's try one together, and then I got one for you all to try. It'll be worth it. So let's make a Turing machine for this language. X with letters A, B, such that X is equal to the reverse of X. This would be the palindromes, if you will. Sorry, it's behind the thing there. X equals the reverse of X. This first part just tells you what letters are, right? X is in the any string on A's and B's, such that X equals the reverse of X, something like A, B, B, A, B, B, A. That's an example of a string that is in this language. X equals the reverse of X. I would like to try and make a Turing machine which accepts only strings that look like that. And just because it is always our general strategy, I want to try and think of this somehow in terms of marking off letters one at a time, until by the time we get to the end, everything is marked, or at least something like that. Would anybody perhaps be able to suggest a strategy that we can use for marking letters in a string like that? I mean, we start off pointing at the first one. I think it's natural to just mark off the first letter. How can we mark letters off accordingly? A little? This thing? Yeah. So all of this is X, and X is equal to its own reverse. That's what the thing says. Idea? Yeah.
Would it be similar to when we did the balanced brackets?
Maybe. Yeah. Similar to the balanced brackets. Yeah, actually this is, sorry, when you said that, for some reason I thought it was something completely different. It is similar to the balanced brackets, although I would say it's quite a bit easier. The problem, what makes the balanced brackets difficult, that was like this. What makes the balanced brackets difficult is if you look at this one, maybe X this one out, how do you tell which is the matching closed bracket? As you move to the right, you might think that this is the matching closed bracket, but it's not in this case. Actually, in this case, you got to go all the way to the end. You may think we're going to have a similar problem. I can mark this A, and then I go over and I'm looking for the A which matches it out. But I think actually I can mark this A off, and then, sorry, the matching one is on the end, right? And I can mark the matching one. Then how about this B? Where's the matching B to that? Well, it's sort of on the end again. In fact, to match each letter, really, you can just always go to the end, and then maybe, I don't mean the very end, maybe go to the very end and then back your way up through some X's, and then this will be the matching letter. So the next step would be X that B and X that B at the end, right? So if I were to write sort of in words the procedure, you mark the first letter, then you go to the end, and you look for that same letter to appear, and you mark it at the end, all right? So I'll say something like mark the first letter. Now in my example, it was an A, but it might be a B. And then you move to the right. Move, can I just say all the way to the right? I mean, until you see a blank. You go all the way to the right, and then you might have to backtrack through a few X's. Start moving to the left as you go through some X's. So move to the left through X's. But then you will arrive at a non-X letter, And if that's the same as the letter that you marked in the first step, then you should mark it again. And then move back to the beginning and start again. So move to the left through X's, and then I'll say if we see the first letter again, mark it, and then move all the way left and start again. This is the basic concept. Mark something off the beginning, go to the end, mark the same thing off at the end, go back to the beginning, do the whole thing again. All right? This,
What happens
yeah.
if, like, in the example we're using, like A, the middle A doesn't have a match? Like, what do we do with that?
Yeah, this is interesting. So this really comes into play at the end. So I was gonna not talk about this until later, but yeah, there are kind of two types of strings that have this format, and it depends if they're even or odd length, right? An even length string will have no leftover thing in the middle, and an odd length string will have a leftover letter in the middle, which has no match to it. Turns out not to be a big deal, but we'll talk about it. Would you mind if we just don't worry about it right now? Let's try and get the basic structure here. I see basically 4 states here. 1, 2, 3, 4, right? You have to isolate sort of the different movement behaviors, and each of those can be described in a different state. But we have a similar problem to what we encountered last time, and that is a bit of complication about this right here. You mark the first letter, and then if we see the first letter again, all right? Anybody remember how we handled that? The problem is you don't know what the first letter is going to be at the beginning. It could be A or a B. And then by the time you get down to that state 3, you have to somehow remember whether it was an A or a B from the first step. Anyone remember how we handled that? Yeah, you split it into sort of 2 parallel paths. One path in which there are like 2 parallel universes. One in which the first thing you saw was an A. So instead of just state 2, I'm going to make state 2A and 2B. The states act exactly the same way. They just have to be separated onto 2 separate tracks so that you can sort of remember in this way whether it was an A or B to begin with. State 3 also needs to be split because the behavior in state 3 depends on what you saw in the first step. Although state 4 doesn't need to be split anymore because by the time you get to state 4, you've already dealt with that single letter and it doesn't matter anymore what it was. All right, let's do it. So I have my basic structure is going to be like 1 goes into sort of this northern track, and then there's also a parallel and more or less the same track going down south of the border, and there's sort of a basic loop like this. All right, this is the basic structure. Now, there's going to be some fancy business to decide when to accept, and this is going to be not terribly fancy, but we do have to think at that point about what about the one leftover letter in the middle? Is that going to be a problem or not? Anyway, let's. 1 is the starting state, so put your starting state out. Okay, what happens in state 1? It says mark off the first letter. Now, just like in all of our other examples involving marking, I'm going to put in this because in later steps, at the beginning this wouldn't happen, but in later steps when you start at the very beginning of the string, there may be some X's left over from previous steps and you have to push past the any initial X's. But anyway, if we see an A, we mark it and move to the right and go into the A track. And if at the beginning we saw a B, we would mark it and go the other way, BXR, into the B track. All right? What about state 2? State 2 just says move all the way to the right. So this is going to move me to the right through any A's or B's or X's until you see a blank. So that's just one of these. AAR. Sorry, I don't have enough room here. BBR, XXR. You remember what I wrote here, right? And then the trigger from 2A to 3A is when we go all the way to the right, past the whole string, and end up at a blank. So here it says blank, blank, L, right? If you go all the way to the end, encountering a blank, move yourself back one. And then in state 3 is when we, first of all, we continue to move left through any x's that might be there. That would be XXL. Keep moving left through any x's at the end, which have already been marked off. And then, if you see the first letter again, which in the upper track is a A, we should mark it. So I'm going to say A, X, and then might as well be L there, because we intend now to go back to the beginning. And in state 4, we just go all the way back to the beginning. So I'm going to do AAL, BBL, XXL. Until we see a blank, which means we're back on the leftmost side. And we start again. So it's a BBR. Means the head moved all the way past the entire string onto the left, hit some blanks, and so it moves back into the first position. All right, that's the upper track. I'm just going to fill in the details for the lower track. So state 2B and state 2A are actually exactly the same. You may wonder, do we really need them to be separated at that point? We do, because they have to be in two separate tracks, because state 3 is actually different. So BBR, AAR. Going across here is a BBL. Sorry, that's a ugly looking BBL. Okay, and then from 3B up to 4 should mark a B. So this is BXL. And I think this is the entire basic machine. All right.
Can you be XXL on the 3B?
Oh, yes, I forgot that. Thank you. Yep. Anything else I forgot? I don't think so. This is the basic behavior of the machine. Now we should think about the end. What will happen once the string is sort of fully marked up and accepted? So in my example, actually, I'm just going to make up another one. How about ABB, BBA? All right, this one is even length, so there will be no leftover letter in the middle. But can we say what exactly will happen if you do this machine to that string? So skipping many, many steps, the first time through the whole big loop, it marks like that. And then the next time through, it will mark off like this. And then the final time through, it will mark off those last two B's. And eventually the head will end up back at the beginning in state 1. And now if we continue to run the machine, the head here in state 1 will just move to the right. It's doing this one, XXR. Move to the right all the way down and encounter a blank, and that should be the signal that the string should be accepted. All right. Now this is only when there's no one extra letter, so we got to talk about that separately. But in the case when there is no extra letter in the middle, that's what will happen, right? We'll be in state 1 and we'll see a blank. And that should be accepting. So this is not the only way to be accepting, but this is one of them. I'm going to say BBR or whatever. It doesn't matter what you say there, but if you see a blank from state 1, it should be accepting. Now, what about if there is an extra letter in the middle? Let's just try to look and see what would happen in that case. That would mean it was like this, I'll write it this way, say. All right, you're gonna, if you go through sort of the steps, skipping many steps, you mark them off like that. The next time through would mark off like that, and then like this. Okay, now is where it gets interesting. You start pointing here. You're in state 1. You go to the right through these X's, and then you end up in state 2A, because you will mark this off. Okay, so what will happen next is that A in the middle will indeed get marked off. Then you're in state 2A here. You're going to move to the right all the way to the end. You will see a blank. Okay. You'll go over to state 3A. 3A says move to the left over and over again through X's. All right. You will go all the way back through and hit a blank. That's when you should accept. So this is, it's not really clear at all. You really have to think this through. But from here also, if you see a blank, it should be accepted. BBL, I don't know why I put L. I usually put BBR, it doesn't matter. But if you see a blank in state 3A, that means the only way to see a blank in that case is if you really had that one extra letter with no match to it. And that should still be accepted. All right, and where else? 3B, the same thing will happen. Like in this example I did, I was in 3A because that letter in the middle was an A. But if the letter in the middle was a B, you'd be down here and the same thing would happen. So another accepting state right there. I feel like my picture had some sort of pleasing symmetry to it, and then I added those two things that wrecked the picture. But sometimes it's how you got to do it. All right. Any thoughts about that? Oh, tricky. Great. Okay, I got one for you all to try, and then we'll do some review stuff for the test. So I would like you to make me a Turing machine for this language. X is in AB star. This is going to be great. The number of A's equals the number of B's. But they could be in any order you like. All right? So it could be something like AA, BA, BB, about like that, right? Just the number of A's is the same as the number of B's. So think about how you would strategize, marking off letter by letter to verify that there are the same number of A's and B's in there, and then see if you can make your machine. It should look vaguely like the one I just did, but really, if you look closely, all the details will be different. Oh, I got a chat. Sorry, I didn't see. I see the chat now. The first language that we did was all strings with x equal x to the r. X equals the reverse of x. I'm trying to answer Ryan's question in the chat. The first example we did was all strings where x is equal to its own reverse. This example is different. Strings where the number of A's equals the number of B's. See all the boys in the Zoom. Plus Courtney. All right, I want to try and go over this. Everybody's doing great. Oh, I see a chat. Why did we have to account for an A, B in between X and X reverse? Okay, let me address the chat before we do this. There was this, in this example, there was this issue of the letter in the middle, which sometimes is there, sometimes it's not. It's because the strings that I'm talking about are ones in which X is equal to X reverse. So this is different from, there are some other examples that we've done in the past which involve strings that themselves look like X followed by X reverse. A string that looks like this is one in which there is no letter in the middle. There's just some stuff followed immediately by the same stuff backwards, right? This is different. This is saying the entire string is equal to its own reversal. So this would, for example, X equal ABA has this property because X reverse is also ABA, right? And then they're the same. So the string ABA does satisfy this formula. Even though ABA itself cannot be written in this format, X followed immediately by X reverse. So ABA is not equal to any string X followed by its own reversal. But these are two different things to talk about. This is the subject of the example that I was doing before. And so we do sometimes need to account for an extra letter in the middle which doesn't match with anything else. Does that answer your question, Ryan? I hope. Yes. All right. He's not speaking to me. That's fine. Okay. Let's talk about this one currently under consideration. The number of A's is equal to the number of B's. All right. I saw lots of great ideas on this. The idea is you mark off the first A. This is going to be state 1. Mark the first, well, not necessarily the first A, although I suppose you could think it through that way. As I was walking around, everybody did the 2 branching paths, which is what I expected you to do. But if you don't like the branching paths, actually you could decide to mark every A and then match it with a B. And that should still work too. It would be a totally different diagram. But anyway, I'm going to mark the first letter, then move to the right until we see the second letter. So I'm going to move right through X's and whatever that first letter was, because I don't, like if I saw an A first, I'm going to move to the right through a bunch of X's and through other A's. Move to the right through X's and first letters, whatever that is, and then mark the other letter. I mean, if I saw an A first, I'm going to mark a B in this step. Or if I saw a B first, I'll mark an A in this step. And then we are going to move all the way left. So really, we only have 3 states here. This one has to be split, 2A and 2B, and 3. And this is the big loop, right? Let's see. So when I draw this on the diagram, I have state 1. It's going to be like this, 2A to 3, and then similar stuff down here. All right, starting in state 1. So first you have to move through X's, which are ones which you've already marked from previous steps. And then if I see an A here, I mark it, AXR. Here I continue to move to the right through any more A's, AAR or X's. Come on now. All right. And if I see a B, I mark it. BX. I might as well say L there because my next order of business is to go all the way back to the beginning of the string. In state 3, I'm moving to the left through everything. AAL, BBL, XXL. And then when I see a blank, I'm back at the beginning. Blank, blank, R. All right. I think as I was going around, pretty much everybody was settling on something like this. And then the bottom track is very similar. It says BXR in this spot. And then in this state, I go XXR, BBR, and then I go AXL. And I think that's my whole machine. Any questions so far? I got another chat. Yes. Yeah, he was just answering me from before. Thank you for that. affirmation. Feel free to shout out, by the way, folks at home. I will probably hear you. I don't always see the chats right away, as you can tell. All right, what about when is it accepted? It's accepted when everything is all exited, and like other examples, that will be detected from here. If you go back to the beginning and they're all X's, you will eventually see a blank in this statement. So my accepting state is like this. And that's that. All right? I am pleased to see, as I'm walking around the room, it seems like most people are getting there. These are, in my opinion, quite a bit more complicated than making like an NFA or DFA or a regular expression or some such. Any more questions about that? This is all I wanted to say about Turing machines, making a Turing machine that does this or that. Excellent. All right, we've only got 20 minutes left, but that's enough time to talk about the test a little bit. Let's do it. So I made up sort of a list of topics, and then we can, if anybody wants to, refresh our memory about this or that, we can do examples from any one of these sections. I hope 20 minutes is enough time. Of course, if you have more questions over the next couple of days, feel free to email me, and I'd be happy to respond. Okay, so topics. The first topic, and this, when I looked at this, I was shocked how long ago this was. The last thing from before, and the first thing we talked about after the first exam was the converting an NFA into a regular expression. Can you believe it? We were so young then. All right. Converting an NFA into a regular expression. This is not terribly hard. You have to remember how to do it, though. Okay, and then we talked about derivatives. Remember that? Derivatives. The Brzozowski derivative. This is how you show that a language is not regular. Again, something that is worth looking at since we haven't done that in such a long time. Okay, then we talked about basics of grammars, which probably you already remember pretty well. Then we talked about building a context-free grammar. Building a context-free grammar. Like I give you a language, you tell me a grammar for that language. You have to remember strategies for like remember how to do something like this. For balancing, matching exponents like that. You can only match exponents in 2 positions in a context-free language. If there are 3 positions, then it's not context-free. Okay, then we talked about stack machines. And probably the most important thing to remember about stack machines is just the basic idea, how it works. If I show you a stack machine, can you tell me what kinds of things are accepted or not? But a good way to approach that is converting from stack machines back and forth with a context-free grammar. In my opinion, context-free grammars are a lot easier to understand. And so even on the test, if I showed you a stack machine and asked you about it, you might find it helpful to convert it into a grammar. So to me, it's easier to think about grammars than stack machines directly. Okay, then we talked about proving a non-context-free language, proving that something is not a context-free language. The argument is basically the same every time, although you have to remember how to do it. It involves that U, V, W, X, Y thing with the parse tree. And then the very last thing was basics about Turing machines. So I might say, here's a language, you give me a Turing machine for that. Similar to the ones that were on the homework due today. All right, these are all the topics. What do you want to talk about for our remaining time? Maybe you have a particular thing you want to try an example of? They probably will. That's true. You want to push the Turing? I just broke my pencil. I unscrewed the tip. Put it back on. I'm not gonna. Not like a big one like this kind of thing. I wouldn't. I would say ones that are similar to the one on the homework. The ones on the homework. They were hard on the homework? I thought the last one was. I thought the last one was hard. The first four also? Easy Turing machines might be on the test. I mean, no more than one, because we got all this other stuff too. So it definitely will not be like a major thing on the test. But we could talk about those ones on the homework that I thought were easy, if you didn't think they were easy. Do you want to talk about any of those? Yeah?
Yeah, I think all of them.
How about the first one? It said, trying to remember, AX?
Yeah. Yeah, I
So that one is actually very easy if you think about it properly. Did you feel like it was very easy? What did you say for that? I don't want to give away the answers here.
I didn't think like what about when like X is C is X
Okay.
X has to be
Yeah, that one.
What was it? Oh, the length of X is
less than 3.
less than 3. Okay, my strategy for that is, so X has to look something like ABA, or maybe AB, something. Here's in words. The machine should start where at the beginning, move to the right 3 times, and if it's a blank, accept. That's it, right? Like it doesn't even matter what the letters are in the string to begin with. Just make a machine that moves to the right 3 times. Now, how do you make it move to the right 3 times? We know how to make it move to the right over and over again, but exactly 3 times, you can just make 3 states, each of which moves to the right once. So no matter what you see, move to the right once. It doesn't go back to itself, because if it went to itself, then it would repeat forever, and you don't want that. This is my hint for that one.
So can the string be 3 letters, or can it only be?
Oh, less. Yeah. Okay. So less than 3. Yeah. It actually can't be that. So then maybe you only need to move 2 times. Right. Move twice to the right, and then see if it's a blank. I heard somebody say something here, but I couldn't hear very well. You say it again.
I was just saying that it has to be 2 letters, correct? Because it's
Yeah.
less than
Right.
not less
Yeah. That was my mistake. Sorry, my volume is. That's not what I wanted. I want my zoom. Yeah. My zoom volume defaults to the middle. What else can we say? Did you want hints for the other ones?
Yeah, the DFA one. I'm stuck on.
Okay. So the hint for that, I mean, I said the hint. The idea is, like, for example, if I had, this is a DFA which accepts whenever there's a, this accepts something like a to the 3n, right? This is the starting state and also an accepting state. So the idea from the point of view of a Turing machine, what you have is something that looks like this, say 6 A's, and the Turing machine begins pointing at this A. So my hint was use the same states in the same arrangement, but always move to the right. Now, you have to change something about the accepting states, but use the same states in the same arrangement. Always move to the right. So instead of like this letter, or this arrow here, A, instead of an A, I said keep it the same on the tape and always move to the right. So I'm going to turn that into an AAR. So what it does is it is pointing at the A, and it just moves to the right. And the next letter it sees is pointing at an A. And then if I do that to all of them, AAR, AAR, then what I have is this Turing machine is just going to go down the list here and move from one state to the next as it moves to the right in the string. And eventually it gets to the end, which will be a blank, and that is your trigger over here to see where the accepting states should go. So basically, if you see a blank from here, then it should be accepted. If you see a blank from the other two states, then it should not be accepted. So I would take this diagram and insert, like we usually do, an extra sort of arrow going off from one or more of these states into an accepting state. Yeah, you want basically the same diagram, although you're going to add more accepting states, but the other states should be the same number. Yeah. My more explicit hint. What else? Do you want to talk about one of these old topics? I mean, we can talk about the homework exclusively, but the Turing machines, you should not expect to be a major source of focus on the test.
Stack machines where we all always say if the empty string. We would give an example. It was like examples of republish A, S, S, X, and then E, X, empty string.
Okay.
I'm trying to, I don't know.
Yeah, there are stack machines like that. So let's try to make a stack machine. Stack them for, how about A to the n, B to the 2n. All right. Like I said before, my approach to this, just because of my own comfortability, would be to first make a grammar and then convert it into a stack machine. Now you could, the answer will always have a very particular format if you do it in that way. You could try to somehow design a stack machine from the ground up, although that to me is quite a bit harder. So maybe we can just try to make a grammar first. I think of this in terms of sort of balancing here, where we need to balance in such a way that we have 2 B's for every 1 A, right? Anybody, can you think of how to make a grammar for that? Two B's for every 1 A. Yeah. A, S, B, B. Great. And then put your or epsilon so that you can finish. So however many times you go through that A, S, B, B, you get 1 A and 2 B's. And they will match up in the way you want them to. And then this I can convert to a stack machine. And this you have to remember the sort of strategy, or it's not much of a strategy, you just have to remember how to write this thing. So I go read, pop, push. And the way to do it is every grammar production becomes an epsilon transition. Epsilon S, A, S, B, B. Epsilon S, epsilon. So anything like, X goes to Y becomes epsilon X, Y, right? And then we also, anybody remember this? There's also more things I need to include in my steps here. Right, you also have these AA epsilon. For each letter in the alphabet, you need something like this. That's it, though. So this will be a stack machine for the original language.
So are we always able to do it that way? Because when we have the homework on stack machines, you had us do it a different way from first.
Yeah, there was one that I said,
I don't like it.
don't do it like this. I'm not going to say that on the test. So it will always be, to do it this way will always be an option for you. Then you feel great. That's good. I feel great too.
Professor, can you do another one where like the exponent variables are different? Where it's like A to the N, B to the M, and then like C to the something?
Sure. So how about A to the N, B to the M, C to the K? This is one in which all three are different. Maybe let's try that. Let's also try A to the n, B to the m, C to the n plus m. And just for fun, let's also try A to the n, B to the n, C to the n. Let's make a stack machine for each one of these. Now, maybe I might as well say right now, one of these is a trick question. Actually, one of them is impossible. Which one is it? Yeah, the last one is impossible to make a stack machine because this is not context-free. All right? Not a context-free language, so you cannot make a stack machine. Not possible on a stack machine. All right? And this might be, what on a stack machines, this might be how I ask a question. I could say, here's a language. If it's context-free, then make me a stack machine for it. And if not, then show that it's not. Right? Anyway, the other two are possible. So can we do grammars for the other two? The first one here, I would say there are many ways you could write the grammar for this, but it just has any number of A's followed by any number of B's followed by any number of C's. Any ideas? What were you going to say? No, we're doing the hair. Okay. Or I don't think you need or epsilon. Maybe.
And then x goes to ax.
Or epsilon. Now you need the or epsilon.
And
Yep.
then y goes to y epsilon.
Great. CZ or epsilon. Excellent. Yeah, so this is a good grammar for that first one. And then this you can turn into a stack machine in the way we did before. So read, pop, push. It would go epsilon s xyz, epsilon x ax, epsilon x epsilon, and so on, right? Epsilon y dy, epsilon y epsilon, epsilon z cz, epsilon z epsilon, and then aa epsilon, bb epsilon, cc epsilon. Excellent. So that's a stack machine. It's kind of long-winded, but that'll do it. And how about the next one? A to the n, b to the m, c to the n plus m. Anyone think of a grammar for that? Here's a hint. I would think of this as this. What? C to the n. That's the same, right? Only it's a little more obvious how to balance them out. The b's and the c's balance, and the a's and the c's balance. So I would do something like S goes to A, S, C. So this, if you do over and over again, you generate the outer A's and the matching C's. And then you do that for a while, and then you switch to something else, say T, and then T makes the inside. So you do the T one a bunch of times to get you the B's and the matching C's on the inside. And then this you can convert.
Can you, for that one, can you do like S goes to S1, S2? And then S1 goes to ASC, and then S2 goes to BSC epsilon?
That's a decent idea, but not quite. So I think this, and then you said S1 goes to like that first one that I did. A, S1, C, or epsilon, and then S2 goes to C, S2, C, or epsilon. What this will do is, so it's kind of like this S1 is going to turn into that, and this S2 is going to turn into this, right? But because of the way you sort of stuck them together, one after another, actually what you get from this is things that look like A to the N, C to the N, B to the M, C to the M, which is different. That's not the same as that, right? It's in a different order.
Thanks.
Yeah, so, I mean, this would also be a decent example that I could make you do, but it's not quite the same as what I said before. Right? Well, this one I was going to write the stack machine, but everybody knows how to convert that to the stack machine, right? Read, pop, push. What? That's not how. Epsilon S, ASC, etc. You know how to do that, right? 2 more minutes. Anything else we can say in 2 more minutes? Just for fun, you want to convert an NFA to a regular expression? It's been a while, right? I'm just going to make up an NFA here. How about this? Here is an NFA. Convert this into a regular expression. The idea is you want to look at paths that you can take from the starting state to the accepting state. In this case, there's sort of one big loop here, right? You can go around this loop. And loops in a regular expression are indicated by the star. So my answer here is actually going to be some whole big bunch of stuff with a star around it, where the inside of those parentheses are sort of a regular expression version of that loop on the inside. And you want to think about, how would I write the letters that make up this loop here? I would say it has to be an A to begin with. I didn't even put a direction on this arrow. Can you believe it? I meant like that. So in order to go around this loop, you got to do A followed by epsilon followed by A, right? But in between those, you could also do A. You could do some B's in here if you want, and then you do epsilon. Then you could do some A's or B's in here if you want, and then you could do A. So it's something like A first, and then maybe you do some B's. So I put a B star there. That means you've got to do this A, and then you can do some B's here if you want to. And then you do epsilon, actually, so if you want, you could put epsilon here, although in a regular expression that doesn't do anything. But anyway, then we have A's and B's here in a loop. That I would indicate, I'm just going to tell you, just because we got to go. That would be something like AB star. That means over and over again, I can do A's or B's in any combination. This is different from A star, B star. That would mean you do some A's followed by some B's, but there's no opportunity to do more A's after the B's, and that's different. And then anyway, followed by a single A. So this is my regular expression. Like I said, that epsilon in there can be omitted. It doesn't change the meaning of the regular expression. All right, and I think that'll do it. Like I said, I'd be happy to respond to emails if you got more questions. Otherwise, I'll see you on Friday. Even you boys.